Here are the sample problems for Class 5 of Math 117. So the first challenge is to make an interval that is open at the left end, closed at the right end, and has an irrational number as its right endpoint. And what we're trying to do is to make this using only the countable collection of intervals that extend from minus infinity up to q, where q is a rational number. So we're allowing ourselves only a countable collection of intervals, and from this we're going to generate a fairly arbitrary Borel set. Okay, the first problem is that the right endpoint is pi, which is not a rational number. And here's how I'm going to solve that problem. I'm going to form an increasing sequence of rational numbers that converges to pi. And the obvious way to do this is to take q1 equals 3.1, q2 equals 3.14, q3 equals 3.141, and so on. Better and better decimal approximations to pi. Then, since in a sigma field I'm allowed to form countable unions, I will take the countably infinite union of intervals that extend from minus infinity up to q sub n, and that's equal to the open interval from minus infinity to pi. Why? Well, it doesn't include pi because pi is not in any of the intervals on the left-hand side, but if x is less than pi, then the value x is going to be contained in one of the intervals on this side. Okay, now the problem is we're supposed to create an interval that's closed at the right-hand endpoint, but you proved in class that you can form countable intersections of elements of a sigma field, and the resulting infinite intersection is still in the sigma field. So what I'm going to do is to argue that in exactly the same way, I'm going to do this first with 1, and then the same thing will work with pi. I can consider intervals that extend up to 1 plus 1 over n. The number 1 is in all such intervals and is therefore included in the infinite intersection. But if I consider any number x that is greater than 1, then it is eventually going to fall outside the interval that goes from minus infinity to 1 plus 1 over n when n gets very large. So nothing bigger than 1 is in the intersection, and I've succeeded in making the right endpoint be closed. Similarly, in exactly the same way, I made an interval whose right endpoint was pi. I can make one whose right endpoint is pi plus 1 over n, and the infinite intersection in that case is going to be the interval from minus infinity to pi. By the way, this interval is a closed interval. At minus infinity and plus infinity, you satisfy the conditions for both an open set and a closed set. So it's legitimate to say this interval is open, this interval is closed. If I want to make this more explicit, it's perfectly legal to write it that way. Okay, we're almost done. All we have to do now is exploit the fact that we can form intersections in a sigma field. And I will take the intersection of the interval that extends from minus infinity up to pi with the complement of the interval that goes from minus infinity to 1. This doesn't include any number that is less than 1 because when I take the complement of this set, I get only numbers that are 1 or larger. It doesn't include any numbers that are larger than pi, but it does include pi, and we've done it. Next problem. Here's a simple game with dice. You roll a die. You get $1 if the roll is odd. You get $10 if the roll is even. And you get a bonus of $5 if the roll is greater than 3. And my first challenge is to write this as a sum of 3 indicator functions. So I take 1 times the indicator function that has the value 1 if the die roll is 1, 3, 5. That takes care of the odd numbers. I add on 10 times the indicator function that has the value 1 if the roll is 2, 4, 6. That takes care of the even numbers. And then for the bonus, I add on 5 times the indicator function that has the value 1 if the die roll is greater than 3. And I've succeeded in writing x as a sum of 3 indicator functions. But I can do better than that. I'm now going to define an equivalence relation by saying that if 2 rolls have the same payoff, the values of the die roll are in the same equivalence class. And this is going to create a nice partition of 1 through 6. It's going to include the set 1, 2, 3, where the payoff is 1, because the number is odd, but it doesn't exceed 3. For 2, the payoff is 10. But for the even numbers 4 and 6, I get the 10 for even plus the bonus of 5, and the payoff is 15. While for 5, the number's odd, so I get the bonus, but it's only added to 1. The payoff is 6, and there's my partition. I've partitioned 1 through 6 into the level sets for the function x, and finally, I can write x as a sum of indicator functions for the sets in this partition. In other words, I can write it in terms of payoff values. It's payoff of 1 times the indicator function for 1, 3, plus a payoff of 10 times the indicator function for 2, plus 15 times the indicator function for the set 4, 6. plus 6 times the indicator function for 5. And this is true quite generally whenever you have a function that takes on only a countable number of values. You can always rewrite it as a sum of indicator functions on the level sets of the function. So now let's extend this idea to a very slightly more challenging situation where we have as our sample space all the real numbers. So now we're dealing with an uncountable sample space. And the function x, we can think of it as a payoff function. We say we're going to generate a random real number. If it's between 0 and 6 inclusive, you get $3. If it's between 4 and 8 inclusive, that'll cost you $5. But if it's between 5 and 7 inclusive, you will get a bonus of $2. And we're going to play exactly the same game that we just played in the case where there were only 6 elements. Now the trick to this is graphing the function. So let's set up our graph. And clearly, if the value is less than 0, the payoff is 0. But the payoff abruptly jumps to 3, and it remains at 3 for values up to but not including 4. At 4, the second term kicks in, this penalty of 5, and the value abruptly drops to -2 and stays there until we get to 5. When we get to 5, the third term kicks in, and we add on another 2, bringing the total payoff to 0 in between 5 and 6. But at 6, our original $3 drops out, and between 6 and 7, the payoff is down to -3. And finally, once we get up to 7, only the penalty of -5 is applicable until we get to 8. Notice the penalty of -5 is there for the value 8, but for values greater than 8, we're back to 0. So we've got a function that can take on only 5 values. In spite of the fact that the domain is uncountably infinite, when we call this a random variable, we'll call it a simple random variable because it takes on only a finite number of values. And each of its level sets is going to be a Borel set. So now we can write down our partition. For value 0, we have a rather messy Borel set. For value 0, we have -infinity to 0, union with the closed interval from 5 to 6, union with the open interval that starts at 8 and extends to infinity. And this is a single set in the partition because all you know is the payoff was 0. You don't know whether it was 0 because the number was negative between 5 and 6 or greater than 8. So only the union of these is in the partition. The other ones are simpler. We get a value 3 from the interval from 0 to 4. We get a value of -2 for the interval from 4 to 5. We get a value of -3 for the open interval from 6 to 7. And finally, we get the value of -5 for the closed interval from 7 to 8. And if I wanted, I could finish this off in exactly the same way as I did the previous example by writing the function x as a sum of multiples of 5 different Borel sets, indicator functions, one for each possible value of the function. Finally, we've got a little proof. This could show up on the midterm exam. I have to define the Borel sigma field